As capacitors store charge, they also store electrical energy. The energy that is stored in a capacitor is equal to the work that's required to move charge onto the plates. So if you hook a capacitor up to a battery, the battery must do work pushing the charges onto the plates. As the plate charges, there is an increase in potential difference across the plates, and it becomes harder and harder to put additional charge on the plates. So if we look at the amount of work, a small amount of work that's done to push a small amount of charge onto the plates, that's going to depend on the potential difference that's currently on the plates. And so the total work that's done to push the charge onto the plates as the potential difference changes is going to be the area under this potential difference versus charge curve. The total amount of work would be equal to this total area, and the area we notice is a triangle. So the area would be 1/2 base, where this is Q, the maximum amount of charge stored on the plates, and times delta V, where delta V is the final potential difference across the plates. Now, if we don't actually know the charge that's on the plates, if what we know is potential difference and the capacitance, we can replace the Q using the definition of capacitance, and Q is equal to capacitance times potential difference. So we find there's actually 3 expressions we can use to figure out how much potential energy has been stored in the capacitor. The amount of potential energy stored in the capacitor is 1/2 Q delta V, where Q is the amount of charge on either plate, delta V is the potential difference across the capacitor, or we could use 1/2 capacitance times potential difference squared, or we can use charge squared over twice the capacitance. And these 2 equations are both derived by taking this initial expression and replacing either the Q or the delta V with the definition of capacitance. So any of these 3 expressions could be used. The one you want to choose is the one that makes your problem the most convenient. So let's practice using one of those expressions. In this example, we have 2 capacitors with capacitances of 1.5 microfarads and 0.25 microfarads, and they are connected in parallel. The system is connected to a 50-volt battery, and we want to know what electrical potential energy is stored in the 1.5 microfarad capacitor. So first, let's draw a circuit diagram showing the arrangement of the capacitors. So we know these capacitors are hooked up to a 50-volt battery, and that we have 2 capacitors that are in parallel. One of the capacitors has a capacitance of 1.5 microfarads, and the other has a capacitance of 0.25 microfarads. So that's what our circuit would look like. And we want to find what is the potential energy stored on this 1.5 microfarad capacitor. So if we just consider this 1.5 microfarad capacitor, we know its capacitance. Its capacitance is 1.5 microfarads. And we also know the potential difference across this capacitor. Because the capacitors are in parallel and they're hooked up to a 50-volt battery, the battery is supplying 50 volts, that's the pump, and then we need a waterfall, whether we go this way or this way, of 50 volts as well. So each of these capacitors has a potential difference of 50 volts. So I can say that the potential difference for my 1.5 microfarad capacitor is equal to 50 volts. So then if I look back at the expressions for finding the potential energy stored in a capacitor, I can see that one of them does depend on just capacitance and voltage, and that is that the potential energy, the potential electrical energy of this capacitor is 1/2 times the capacitance times potential difference squared. So plugging in numbers, that would be 1/2. The capacitance is 1.5 microfarads, that's times 10 to the minus 6. And then the potential difference is 50 volts. Square that, and I get a potential energy then of 1.88 times 10 to the minus 3rd joules, or 1.88 millijoules. That is stored in this capacitor. So that's the amount of energy stored in that capacitor, and if the capacitor discharges, that's the amount of energy that I would get out of that capacitor. So next, let's consider this question. Consider a simple parallel plate capacitor whose plates are given equal and opposite charges and are separated by a distance d. Now suppose the plates are pulled apart until they are separated by a distance of d, which is greater than the initial separation distance. Will the energy stored in the capacitor increase, decrease, or will it remain the same?